And today we're going to cover section 5, and it's going to be on inverses of matrices. So a matrix inverse is going to be similar to what we do um, in mathematics with real numbers. So when we look at matrix inverse, we can first start it and realize that it's comparable to a reciprocal when you talk about real numbers. So when we talk about what we call the multiplicative inverse of real numbers, we know that a multiplicative inverse is a number that when we multiply it by another number equals 1. Okay, so 1 is called the multiplicative identity in this case. Okay, so in real numbers, 1 is the multiplicative identity because whatever you multiply by 1 equals itself. And if you take two numbers, and you multiply them together and you get 1, then those two numbers are inverses of each other. So 1/3 is the inverse of 3, because when you multiply 3 times 1/3, you get 1, because you get 3 over 3. Or if you take 37, then the inverse of 37 is 1 over 37, because 37 times 1 over 37 gives you 1, and so on and so forth. So we know that for every real number there is a unique um, inverse such that those two numbers multiplied together equal 1. Well, in matrix multiplication, we have a similar situation where we can find an inverse matrix where if we multiply a given matrix by its inverse, we will get the multiplicative identity matrix, which is I. We denote it as I. Okay, so I is the identity matrix for multiplication. Okay, and I mentioned this in the last section. When we were talking about this, I introduced the idea of an identity matrix. And so we know down here, this is an identity matrix, is a 2 by 2 matrix that's an identity matrix because we have ones down the diagonal and zeros everywhere else. Okay, so now we're going to use that idea, and it has similar properties to what we would think in real numbers. Okay, not exactly the same, but similar. So we're going to use the definition of the identity matrix to find the multiplicative inverse of any square, and that's the key word. It has to be a square matrix if it has an inverse. So not all square matrices um, have inverses. Okay, so if it does have an inverse, then we should be able to multiply those two matrices, A, and we'll call the other one A inverse, and those should give us the identity matrix. Okay, we're going to talk about that in a little bit. So here's the identity matrix, and the identity matrix, again, if you multiply any matrix by the identity matrix, you should get itself. So if you multiply on the left by I, or if you multiply the matrix on the right by I, you will get the matrix, the original matrix A, back out. Okay, so it doesn't change anything. So the identity matrix doesn't change the other matrix. Just like if you multiply 3 by 1, you get 3 because 1 is the multiplicative identity. It doesn't change the number. Okay, so similarly, the identity matrix, when you multiply any matrix by the identity matrix, it will not change the matrix. Okay, so now, so again, with matrix multiplication, if we take any matrix and if it has an inverse and we multiply these two together, then, and it doesn't matter whether we multiply it this way or whether we multiply it this way, we will get the identity matrix out. And so finding the multiplicative inverse is a very straightforward process, and it uses the techniques that we've already learned. And so what we do is, to obtain what the value of A inverse is for any square matrix, n by n matrix, for which there exists an inverse, okay, then we use the following steps. We form an augmented matrix. And so the augmented matrix is going to have our original matrix A on the left, and we're going to put the identity matrix on the right. And so what we're going to do is we're going to use our elementary row operations, and we're going to keep using our elementary row operations until we get the identity matrix on the left. So we're going to keep transforming A by using our elementary row operations until we get something of the form that we have I, and then we have B, some other matrix over here. Okay, if it's possible to do this, then B is the inverse matrix of A. So B is what we call A inverse. So we denote it this way, and we say that this is A inverse. Okay, and that's all. That's all we have to do. So that's how we find the multiplicative inverse for any matrix if the inverse does exist. So let's find A inverse for this one. Okay, so what we're going to do is we're going to set up the augmented matrix. And so what we write is we write the augmented matrix A with the vertical line I. So this is the way we set it up. Okay, and then what we're going to do is we're going to start changing this one by using our process, right? So using the Gauss-Jordan method, we're going to start transforming this one into the identity matrix. Okay, so we first select the row operations that put a 0 for the first elements in rows 2 and 3. Okay, so the way I would do this is we're going to change this to a 1, okay, first, and then do this. But again, let's go with what they do. So we're going to change these to zeros by using row 1. So we're going to do row 1 plus -2 times row 2. And so that's going to get a -2, a 4. This is going to be 2, and this will be 0, and this will be, oh, hold on. Yeah, this will be 0, this will be -2, and this will be 0. And so what we're going to do is we're going to take this row and add it to this row and then replace the second row. Okay, and then what we're going to do is we're going to do the same thing. We're going to take -3 times row 1. Okay, so we're going to take -3 times row 1. Okay, and then we're going to add it to 2 times row 3. And so we're going to get -6 and +6 here, and those are going to go away, and then we're going to do the same thing. And again, we're going to go all the way across with our multiplication, okay, and then we're going to add. And then we're going to replace row 3 with the results here. So we get zeros in the first column except for this one. This one will be a 2. Okay, so this is what we end up with. Okay. Now what we're going to do is we're going to work on row 2, or excuse me, work on column 2. So now what we're going to want to do is we want to get this to be 0 and this to be 0 by using row 2. Okay, so what we're going to do is we're going to do -3 times row 2 plus 7 times row 1. Okay, so we're going to add those two and then replace row 1 with that. Okay, so the purpose of doing this is to get rid of this 3. And then we're going to do the same thing with the third row, is we're going to multiply the second row by 3 and the third row by 7, and then replace that row 3 but with whatever this is. Okay, and so now we get zeros here, and now look how this is changing on this side as we get closer and closer to this being the identity matrix. Okay, now we're going to work on row 3. And so now we're going to get rid of these two. And so we're going to do row 3 plus 8 times row 1, because we're going to get a -16 if we do that. So that'll get rid of this one. And then we're going to replace row 1, or excuse me, it'll get rid of this one. We'll replace row 1 with this. And it's not going to change anything here. Okay, or it's going to get rid of this -2. Okay, so the -2 will go away, and then we do the same thing for row 2. So we're going to take 3 times row 3 plus 16 times row 2, and then we're going to take that and replace row 2 with it. And so now notice how this is changing here. This will change again, and this will become closer to the identity matrix. So now this is what we get. So now we got zeros here, and we got the only numbers down the diagonal, and this is what we have so far on the right. So now all we have to do now is divide by 112 here, divide by a negative 112, and divide by 16 all the way across, and we're done. And so this is what they do. And so now we got the identity matrix here, and now we end up with this matrix over here. And this then is the inverse matrix. Okay, and of course we always want to simplify things in lowest terms when we're dealing with fractions. Okay, so now we're done because our A inverse is what's left over on the right hand side. And so here we found the inverse matrix. Now on the calculator we can do the same thing. It's very easy on the calculator. The only thing you do is once you plug in your A matrix into the matrix under edit, under your matrix menu, then all you have to do is actually just go and select A inverse under your math options for matrix under your matrix menu, and then all you have to do is go under math options for fractions to change all the things to fractions and hit enter, and you're done, and it gives you the identity inverse matrix. It's that easy. Okay, but make sure you're able to do this by hand because you will be required to calculate these by hand as well as the calculator. Okay, so make sure you practice both, but it is important to know to do this by hand. Okay, now oops, did I oh okay oh okay, right. So instead of using the Gauss-Jordan method that we learned in 2.2, what we can do is now we can set up the matrix equation that we can solve. And the matrix equation is going to be AX equals B, where this is the given matrix, this is the matrix of variables, and this is the matrix that we're trying to solve for. Okay, and so A is the matrix of the coefficients of the variables, okay, which is what we call the coefficient matrix. X is the matrix of the variables that we're using, that we're given, and B is the matrix of the constants. Okay, and so we could set up equations like this. Okay, to solve this, we need to basically solve for x, and what I mean by that is we need to figure out what the matrix values are for x, because x is the variables, right? Variable matrix, the matrix of all the variables. So if we multiply both sides by the inverse, notice that if we multiply both sides by the inverse here and here, so if we multiply on the left, we have to multiply on the left here. But if we do that, then what we end up doing is remember, the inverse times its the inverse matrix times its original matrix is going to equal the identity matrix, and the identity matrix times any matrix gives the matrix. So basically, we're going to end up with x on the left. And then on the right, we're going to end up with x inverse, excuse me, not x inverse, A inverse times B. And so this is what we're solving for. So if the inverse exists, then we can solve for the system of equations. Okay? And if that's the case, then we can solve for this, and we know that the variable matrix is going to be equal to this. So the solution for the variables comes down to just this multiplication, okay, which we'll see in a few minutes. So now solving the system of ax plus b using matrix inverses. So to solve the system of equations ax plus b, where A is a square matrix of coefficients and A inverse exists, X is the matrix of variables and B is the matrix of constants. First find A inverse of X, or excuse me, A inverse. Okay. Once you find A inverse, then all you have to do is to find X is just multiply B by A inverse on the left. Okay. And the side does matter. Okay. Be careful of that. So now let's use this to use the inverse. Let's use the inverse to find the um, this linear system. Okay, so now again, there's different ways we've done it. Let's use the coefficient matrix. So the coefficient matrix is going to be what, 5, 4, 4, -3. Okay, and then our variable matrix is going to be xy, and then our constant matrix is going to be 23, 6. Okay, so to represent the matrix equations, we're going to use A. So this is our A matrix, which is the matrix of coefficients. Here's our variable matrix. And if you multiply these together, you get this right here. So it makes sense that this makes sense, because if you go back to matrix multiplication and you multiply the coefficient matrix by this matrix here, you get this system right here. Okay, and then B is going to be this matrix here. And so we can write this system of equations equivalently as this. And so now the first step is let's find the inverse matrix. And so we set up our inverse matrix. And so we know that AX equals this, which equals this, which is equal to this, which equals B. Okay, so to solve this, we're going to find the inverse matrix. Okay, so we're going to set up our augmented matrix, and we're going to find the A inverse by doing the same process, the elementary row operations, until we get the identity matrix on the left, and then whatever's on the right is the inverse matrix. So in this case here, the result of A inverse is 3/31, 4/31, 4/31, and -5/31. And so now what we're going to do is, once we have our inverse matrix, now it's just multiplication. We're going to take our inverse matrix and multiply it by B. And that's going to give us our answers, our solutions. So when we do that, we get this. We get 3, 2. We get the column matrix of 3, 2. And so this means that our variable matrix xy equals 3, 2. So the solution is the point 3, 2. And we're done. Okay, easy peasy lemon squeezy, as my 8-year-old says. Okay, now what about this one? Here's an example of fertilizer. So there are 3 brands of fertilizer available. Then they provide nitrogen, for phosphoric acid, and soluble potash to the soil. One bag of each brand provides the following units of each nutrient. So we have this brand, and this brand. So we got Fertifun, Big Grow, and Soakum. So in Fertibrand, we have these units of the minerals. Okay, Big Grow, these are, and then Soakum is these. Okay, so now, but here's the thing. This is what each brand gives in, let's say, one bag of their fertilizer, let's say. Well, different farms require different amounts of the different nutrients for optimum growth, right? So let's say we have 3 farms in 3 different regions, let's say Michigan, California, and Kansas, that require different amounts of nitrogen, phosphoric acid, and potash for ideal growth. So let's say these are the different amounts of the nutrients that are needed on each farm in each area. Well, using the other methods that we've learned up to this section, we'd have to set up 3 different systems and solve the 3 systems separately, right? Well, with the matrix equations that we can set up now, we can solve for all 3 of them pretty much at the same time. And it's much easier. So let's consider the system. So here's the system. So this is the system where, hey, we're going to use for each brand, right? So this is the amount of nitrogen, phosphoric acid, and potash for brand A, right, or brand X. And then we have brand Y, right? And then we have brand Z. And these are the amounts of nitrogen, phosphoric acid, and potash for each one. Okay, and so we know that this system of equations can solve for the number of units of each brand, or the amounts of each brand that are needed. Okay, so and the A, B, and C are going to be constants. Okay, so where A, B, and C are the units of nitrogen, phosphoric acid, and potash needed for different farms. So this is going to be what's going to be changing, right? So let's say we go to Michigan. So Michigan needs these units, right? So this would be 18, 23, and 13. So 18 would be A, 23 would be B, and 13 would be C. Okay, so so what we would do is fill these in. Okay, but let's hold off and not do that right now. Let's leave it in this form because again, different farms are going to have different amounts that are needed. So what we're going to do is let's set up this system of equations instead of as a matrix equation. So if AX equals B, okay, so A is going to be our coefficient matrix, which we get from here. X is our variable matrix, which we get from XYZ. And then B is going to be the matrix that has the different values depending on the farm. Okay, so the first thing we're going to do is find the inverse matrix. Once we find the inverse matrix using A, then we know that the variables, the solution for the variables is going to be just taking the inverse matrix times B, which again is going to change for different farms. So now we have a formula, if you will, that we can say, hey, regardless of the farm that we go to, we can use this calculation and immediately figure out how much of each one they need. So how many bags of brand the first brand, second brand, third brand, right? Because they're going to have to take all of those brands together to get the proper nutrients. Okay. So again, try this. The solution is in the textbook. Try to do it on your own using this information and see if you get the correct answer. If you don't get the correct answer, go to the solution in the textbook, the example in the textbook, and see where you made your mistake. If you still can't figure it out, just let me know. We can work it through in class and figure it out together. Again, make sure you write down your questions and bring those questions to class. That's what class is going to be for. Okay, so now what about cryptography? Now this is another cool kind of use of matrix. It's for coding, encoding and decoding, right? So let's say we want to, cryptography is the study of coding. It's used a lot in security, especially email security, website security, financial security, anything that has to be secured. A lot of this is done in cryptography is being able to uh, have data securely transferred over the internet or vice versa, whatever you have. Okay, so in this case here, we use a very simple way of encoding a message. Okay, sorry about that. I got a little distracted. Okay, so we're going to encode a message. So part A says, okay, we're going to encode a message. Behold. So what we're going to do is we're going to use a matrix. So we're given a matrix and we are going to use its inverse, the matrix A and A inverse, to do the following. So we're going to encode the message behold. Okay, so let's say we want to encode a message that we want to hand to somebody. And so we want to encode it so that if anybody else accidentally or steals the message, they won't be able to read it, or they won't be able to unlock it unless they have the key. Okay, so, and if you ever watch any of these shows like Blacklist or Blind Spot, sometimes they'll use these keys, and they use them differently. There's all kinds of keys, but this is one way of having a key to decode a message. So in the part A, we're going to encode a message. So we're going to take a message and we're going to make it into a code by using a matrix. Okay, so we're going to use matrix A to do that. Okay, so we're going to use this matrix to change this word into a series of numbers. Well, how do we do that? Well, we got to start by figuring out how are we going to represent each letter. Well, easy way to do that is just give them a number based on the position in the alphabet. So A would be number 1, B would be 2, C would be 3, D is 4, E is 5, and so on and so forth. Okay, so let's, first of all, since this is a 3 by 3 matrix, we need to have, if we're going to do matrix multiplication, we need to make sure that the number of columns in the first matrix is the same as the number of rows in the second matrix. So we're going to have to split this up into two pieces of 3. Okay, so let's take BEH and OLD separately. So in this case, we're going to represent BEH as 2, 5, 8 and OLD as 15, 12, and 4. Okay, now what we're going to do is we're going to take A and we're going to multiply A. We're going to multiply each one of these column vectors by A and watch what happens. So if you do that, you get 49, 33, 26 for the first one, and 67, 54, 88. So these sets of numbers represent the word behold. And so you would give the code in this order because each number represents a letter. And so this represents B, this represents E and H and OLD. Okay, so now the only way that somebody would be able to unlock this is if they knew the key, which would be the inverse. So the inverse matrix undoes, remember, inverses undo, right? So that's why they're called inverses, like inverse operations, multiplication and division, right? Multiplication and division are we call inverse operations because they undo each other. So if you multiply a number by 3, right? Let's say you take 5 and you multiply by 3 and you get 15, right? Well, if you want to undo it, if you give that number 15 to somebody and say, well, what was the original number? They're going to say, well, I don't know. It could be 3, it could be 5, it could be 15, it could be 1, right? So I don't know unless you tell me what the key is. So if I say, okay, well, the key is 3, and I'm multiplied by 3 to get 15, then you say, well, the original number was 5. Okay. Similarly here. So if we use the matrix A to get this sequence of numbers, then we can use the inverse matrix and again split it up into 3s, and the inverse matrix will undo what the matrix A did. Okay, so let's do that. So let's say we want to decode this message, and so this is a different message, and it used the same matrices, okay, A and A inverse. So let's decode this one. So what we're going to do is split this up into 3 pieces, right? We're going to first 3 numbers and the second 3 numbers. And now what we're going to do is we're going to multiply on the left by the inverse matrix. Okay. And so if we multiply by the inverse matrix, look what we get. We get 13, 1, and 20, which each number represents the position in the alphabet. And so 13 is M, 1 is A, and 20 is T. And so you get MAT. And then if you do the same thing on the second one, you get 18, 9, and 24, which corresponds to RIX. And so the decoded matrix, or excuse me, the decoded message is the word matrix. And that's it. That's how another use of matrix multiplication in solving for a matrix equation is for cryptography. Okay, that's it. So remember, please make sure you go through and for extra practice and extra is read the textbook. Always read the textbook. There are other examples that you can use and try out in the textbook. Please do those for extra practice. If you have any questions, write those questions down for class and bring them with you. Other than that, practice. Practice the exercises at the end of the section. The more you practice, the better you're going to get at this stuff. And come to class ready to practice, ready to ask questions, and ready to engage. Okay? So until then, have a great day.